What I'm going to tell you a bit about is my work using neuroeconomics to understand addiction. First, my disclosures. I do get research funding from NIH, CIHR, provincial and federal Canadian organizations, and Homewood Research Institute, but I don't have any conflicts of interest with any of the data that I'm going to present today. I also want to start by acknowledging a large group of collaborators that I work with. A lot of the work I'll present today is really team science that we do together. In particular, I want to highlight a couple of people. At the Peterborough Center for Addictions Research, Michael Amlung is an assistant professor there and has been instrumental to a lot of the work I'll present. I've been working with Larry Sweet now for over a decade, applying neuroeconomics to addiction, and he's a critical contributor. And my students, Josh Gray and Max Owens, are also key people who have led some of the studies that I'll present today. And just to sort of give this some context, I'm going to present work that is not necessarily representative of the entire canon of neuroeconomics at this point. It's very representative of what my lab is up to, including some preliminary results and some teasers for future things that are coming down the pike too. I hope you have some interesting feedback. And I also hope to introduce people to behavioral economics and neuroeconomics, because these are slightly esoteric areas of the field. Some people may be familiar with them, some people may not be. So that's my first part of the talk today. What is behavioral economics and neuroeconomics? Then really the meat of the presentation is going to be on two kinds of decision making. Decision making about immediate versus delayed rewards, delayed discounting, and decisions for either to choose to use a drug or not use a drug at escalating levels of cost or drug demand. And then I'm going to offer some conclusions and some future directions for the field, or at least this line of work as I see it. So to get started, behavioral economics and neuroeconomics, behavioral economics is really most simply understood as the intersection of psychology and economics. It's often using economic methodologies to understand psychological processes, or using psychological principles to understand economic decision making. In the big picture, if we think about macroeconomics as being focused on aggregated indicators economically like GDP and unemployment, and microeconomics being focused on families, businesses, and people making transactions with the world around them, behavioral economics is really focusing on individuals as the unit of analysis, and individuals as autonomous agents making decisions and expending finite resources, be they money, time, energy, or other commodities. Neuroeconomics is quite simply the further hybridization of psychology and economics with cognitive neuroscience to go one level deeper within the individual as the agent, and to look at what the brain is doing during these decision-making processes. And another thing to emphasize about behavioral economics is it's not really a field the way we think of field. It's not a discrete set of paradigms per se. It really is a number of different lines of inquiry. So some people will ask me, you do behavioral economics, do you do a lot of game theory? Not really. Game theory is probably one of the oldest forms of behavioral economics. It's focused on really foundational work that came out of the 1940s, looking at how individuals interact to make decisions together, to collaborate, or sometimes to defect. It's very well known because of John Nash's Nash equilibria, which won the Nobel Prize and was the focus of the movie A Beautiful Mind, and is still being pioneered by great work by people like Reed Montague and Colin Kammerer, who are now hybridizing game theory with neuroimaging to understand what's happening in the brain when people make decisions about cooperation. But it's not really the kind of behavioral economics that's applied to addiction. Equally, there's another form of behavioral economics, often referred to as decision theory, which is really the intersection of cognitive psychology and economic decision making. Many people are familiar with Kahneman and Tversky and prospect theory, loss aversion, that is systematic forms of decision-making bias when people are making choices, particularly losses looming larger than gains, that is people being particularly sensitive to losing rewards rather than gaining rewards. And that also is being pushed forward in terms of not just behavioral findings, but also neuroimaging findings, but is largely outside of the purview of applications to addiction. The work that is most pertinent to addiction really comes out of an operant learning framework in which we are interested in addictive drugs as maladaptive reinforcers, both positive and negative, and uses microeconomic principles to better understand maladaptive reward/reinforcement learning. It was originally took its roots out of Bernstein's matching law and was extended by Howard Rachlin, Steve Hirsch, and George Ainsley. Nowadays, it's most identified with people like Steve Higgins, Warren Bickel, Nancy Petrie, who really applied it in ways that created contingency management and voucher-based treatments for addiction, and also developed novel decision-making tasks that are also taking place in my lab, Jim Murphy's lab, and we also are part of a small group of people who use neuroimaging to understand what the brain is doing when these kinds of behavioral economic decisions are being made. So these are kind of the three tribes of behavioral economics. I really come from the tribe that comes from a behavioral reinforcement learning background. But we do have commonalities also. Fundamentally, we all study transactions that people make with the world around them. We integrate psychology and economics to study how people attribute value to things, the choices they make, and really decision making more broadly. And we're particularly interested in understanding rationality and irrationality. Some of you may be familiar that within economics, a common assumption is that of the rational actor, or homo economicus. Behavioral economics takes the perspective that actually a rational actor is a bad assumption because we are mostly irrational. And so it seeks to understand the nature of irrationality. And addiction can be understood in some ways as being a highly irrational psychiatric disorder. Neuroeconomics, again, integrates behavioral economics with cognitive neuroscience to try to understand what's happening in the brain during rational and irrational decision making and what profiles of brain activity are associated with healthy and unhealthy behavior. One more point before I get started with some of the data. The approach that I use in my lab is a translational approach to addiction research. The Peterborough Center for Addictions Research is really exclusively a research center, but we are housed within a large psychiatric hospital. And we really think of ourselves as having one foot in the research world, but also one foot in the clinical world to the extent that we want to do work that's clinically informative. I'm a clinical psychologist by training, and so a lot of what we try to do uses this translational approach in which we try to first study behavioral characteristics, behavioral phenotypes in the lab, but also apply them to clinical questions, unpack them using cognitive neuroscience, and then use them also as novel phenotypes for understanding genetic contributions to addiction. We use lots of different tools. So for example, in terms of our behavioral science work, we have a bar laboratory where we can do alcohol self-administration. We can look at the effects of cues on decision making. We can look at alcohol challenges. And so we can look very, very closely at individual behavior in vivo. In addition, we're increasingly going outside the laboratory, and so we're doing more research using platforms like Amazon MTurk to collect data using crowdsourcing. We have a collaboration with 23andMe, the personal genomics company, in which we've been deploying our decision-making tools within their large cohort of genotype customers. And so we think of behavioral science as not being restricted just to the lab or survey-based design, but also going beyond that. For the purposes of today's talk, I'm really going to focus on this far end of the spectrum. In terms of our imaging work, we primarily do task-based fMRI, resting state fMRI, structural morphometric characteristics associated with decision making. And we've also been working with a physicist at McMaster who's developed a new assay for measuring intracortical myelin. And most people think of myelination as being primarily within the white matter tracts in the brain, but interestingly, cortex also has myelin. And so now we're starting to probe whether or not the myelin within cortex is also associated with substance use disorders. Today, I'm primarily going to focus on task-based fMRI and structural morphometry. Okay, so let's get started. So the first decision-making process I'm going to talk about is delay discounting and addictive behavior. And delay discounting may be familiar to some people here in the form of the famous Michell Marshmallow test. That is the test that's used typically in 4-year-olds to see their capacity to delay gratification by either offering 1 marshmallow now or 2 marshmallows when the experimenter returns in a few minutes. And what's fascinating about this paradigm is that there's a broad distribution of performance. Some kids are really good at it, they do great. Some kids just immediately eat the first marshmallow right away. And other kids will try, but eventually break down and eat the marshmallow. And so there's this really interesting Gaussian distribution of performance on this task, and it's been shown to be highly predictive over time of subsequent outcomes, including academic performance in grade school, SAT score at age 16, substance use outcomes, and other self-control outcomes even in the mid-30s. So this has been a developmental psychology paradigm focusing on delay of gratification. It's really been highly informative, and is very similar to what we mean by delay discounting in behavioral economics. And to operationalize delay discounting, what I mean by this is it's the amount that a person discounts a reward based on its delay in time. That is, how much a reward loses value because it's in the future rather than in the present, and can also be thought of as the extent to which a person prefers smaller, sooner rewards relative to larger, later rewards. It's typically measured using extended decision-making tasks in which lots of different items are presented, all more or less in the same format, to titrate and find the person's precise preferences. So typically the items on these tasks would be things like, would you rather have a certain smaller amount today or a larger amount after delay in time, A amount today versus B amount in C days. So for example, one item might be, would you rather have $99 today or $100 in 2 months? And by show of hands, who would rather have $99 today versus $100 in 60 days? Virtually everyone would not be willing to wait 2 months for $1. But another sample item would be, would you rather have $1 today or $100 in 2 months? And again, by show of hands, who here would rather take the dollar today? No one will really fess up to this because of demand characteristics, I know, but the reality is, in general, most people would not be willing to give up 99% of a reward to get it today, not in 2 months. And somewhere between $99 and $1, there's what we call the point of indifference. There is a value that reflects the amount today that is equal to the larger amount in 2 months. And that difference between the amount today versus the amount in 2 months is the discounted utility of the delayed reward, and that's how much it's being discounted. So then what we do is we look at those points of indifference across lots of different delays, and we can then map the gradient of that decrease using various different approaches. The most common one is this hyperbolic discounting equation that came out of Jim Mazur's lab. There are various other strategies that can be applied, hyperboloid equations, and model-free area under the curve. I have found in my lab that they tend to generate relatively similar results, but fundamentally, the most important thing is that what we're trying to do is, and these are just prototypic data, we are looking at these points of indifference. These are the indifference points at different delays in time on the x-axis, and we can then string them together and model this decelerating function to get a sense of the person's overall temporal discounting function. So we're less interested in preferences for any given time period and more interested in the overall pattern of preferences that the person's expressing for this reward. And in terms of what this reflects phenotypically, I'm going to show you a lot of discounting functions. The steeper the curve, the more impulsive the person is. That is, the more precipitously a person devalues future rewards, the steeper their discounting curve will be. So the steeper curve here is the more impulsive curve. And what we find when we look behaviorally, those were all prototypic data before, but these are actual data. They're from my lab. This is from a study on drinkers. And what we find is, in this case, among heavy drinkers, when we bin them into individuals in the upper and lower 25th percent of alcohol use disorder symptoms, we see that individuals who are higher severity show steeper discounting curves. And this is a finding, came out now 7 years ago. It's very compatible with lots of other similar findings. Here are the data that I showed you before. Here we have smokers compared to never smokers and ex-smokers showing much steeper discounting curves. Individuals with alcohol use disorder from Nancy Petrie's lab, again showing very steep discounting curves compared to controls. Opioid-dependent individuals showing very steep discounting compared to controls. Methamphetamine dependence, pathological gamblers, and potential pathological gamblers compared to controls. So there's this very common behavioral topography across studies. In my lab, we're very interested in reproducibility in our paradigm. So we've done a number of meta-analyses. And these are the findings from a meta-analysis we did that came out in 2011. We aggregated case control findings across the literature using the PRISMA guidelines for identifying studies. We identified 64 studies that actually were comprising over 56,000 total participants. And then we analyzed case control differences across studies. And to break this down for you, in terms of the overall findings, what we found, wherever you see a green circle, there's a statistically significant difference in terms of the effect size comparing criterion positive addiction individuals to a control group. We found overall there was a median effect size difference, about half a standard deviation, Cohen's d of 0.5. We then parsed our sample of studies in a number of different ways. We looked at what we refer to as the primary sample, which were studies that were all using very common methods, these iterative decision-making tasks that I described before. And you can see there that when you have slightly more common homogeneity in terms of assessment, the effect size went up by about 10%. We also found, interestingly, that when you grouped the studies by whether they had a clinical assessment for diagnosis versus controls, versus a subclinical criterion, like a cutoff score on a screening measure, we saw a significant difference in effect size. There was a significantly larger effect for studies using clinical measures. And then when we broke the different studies down, both by clinical and subclinical measures and also by different substance use, we saw that in general, the patterns were common across addictive behaviors. The largest effect was actually for stimulant addiction, but these were generally all in the same area, with one very interesting exception. For some reason, cannabis use disorder was not associated with elevated impulsivity in terms of delayed discounting. There were not many studies in this domain, and more have been done subsequently. But nonetheless, this is the odd man out. We also saw somewhat weaker effects for pathological gambling studies when looking at the subclinical ones. But on balance, we also found no evidence of publication bias. We found that when we did jackknife analyses removing one study, the effect sizes didn't move around very much. And so in general, this seems to be a robust correlate of addictive behavior using case control designs. We recently did a dimensional meta-analysis looking at correlations in the literature, and we were able to aggregate about 11,000 participants across more than 70 studies and found similarly a highly significant association across studies, p less than 10 to the negative 14th in that case. So it seems to be very robust in dimensional studies also. And we've increasingly turned our attention to ADHD and obesity. My students have learned how to do meta-analyses, and so we've kind of gone to the races doing meta-analyses. And so what we found in case control studies of individuals with ADHD versus controls was that, again, we see this is a 0, which would be no difference. In general, you see the pattern of findings is all to the right of 0, with most of the studies having error bars not overlapping with 0. The aggregated effect size was a d of 0.43, so approaching half a standard deviation, highly statistically significant in about 4,000 people. And then for obesity, we were able to use both case control studies and dimensional studies using BMI as our indicator. And here we were able to aggregate data from about 10,000 people. Somewhat remarkably, we identified the same effect size as for ADHD, 0.43. And again, this is highly significant. So from our standpoint, at least in terms of these overconsumption and self-regulation disorders, this is a very stable feature. What I think is very interesting about discounting is it's also highly connected to other health behaviors. So, for example, it's associated with, or inversely associated with, disease prevention behaviors. So cardiovascular testing, cancer prevention, getting a flu shot, exercising, seeing a dentist. These are all characteristics that health economists have linked to discounting preferences. And what I think is one of the most interesting set of findings is that, yeah.
In terms of what each of these tasks itself, is it the exact same task we're talking about, or are each of these the tasks related to the group that you're looking at? In other words, $100 is not $100 for everybody. So is it the exact same task, or is this across a variety of different kinds of delayed discounting tasks?
So that's a good question. There's definitely methodological heterogeneity. There are different tasks, but there are also common ones that are the most widely used. So for example, there's a 27 item and monetary choice questionnaire, also referred to as the Kirby, that is probably the most widely used brief measure. And then there's the typical extended delayed discounting task that are most widely used. But there are, in some cases, especially in the health economics literature, there are more atypical measures, maybe 4 or 5 questions, for example. So it's not completely uniform, but I would say that there are a small number of paradigms that are very widely used. So one of the things that I think is particularly interesting is that there are inverse relationships with anorexia nervosa, particularly the restricting type, aspects of major depressive disorder, and also obsessive compulsive personality disorder. So this isn't exclusively a one-dimensional phenotype, to the extent that extreme performance either towards impulsivity or restraint seems to be associated with adverse health behaviors. And that's really how we think about this in my group now, that this is a dimensional characteristic. It's basically Gaussian. If you're at the far end of the curve, you're likely to be exhibiting aspects, you're at greater risk for conditions like addiction, ADHD, perhaps obesity, but also other more normative things like debt would fall up in the low end of self-control, whereas higher self-control in terms of discounting would be associated with exercise, getting health screenings. But you can, again, go into a pathological level of over-control also. So we see this as very much a trans-diagnostic, dimensional measure of self-control. So what's happening under the hood when people are making these decisions? That's the big question from a neuroeconomic standpoint. Behaviorally, we see very robust findings, and this work really launched to a large extent with a paper by Sam McClure coming out of Jonathan Cohen's lab in 2004. That was the first study looking at neurocorrelative delayed discounting using fMRI. And to step back for a second, neuroeconomics really took off in the early 2000s with studies like this, because these were the first instances in which people took loss aversion, delayed discounting, or game theory concepts and said, we can actually study these using neuroimaging and identify what's happening at all. These were not necessarily in clinical populations. These were largely in normative, often undergraduate human subjects pools populations, but they were proof of concept that you can study these kinds of phenomena. And remarkably, a lot of those early findings have actually borne out. So critical regions included dorsolateral prefrontal cortex, posterior parietal cortex, posterior cingulate, ventral striatum, medial PFC. And this really launched a wave of investigations using fMRI into delayed discounting using fMRI. And in my own lab, it gave rise to a study focusing specifically on neurocorrelative discounting in individuals with alcohol use disorders. So this was a relatively small study, 25 people. The AUD negative individuals were relatively carefully matched to our AUD positive individuals. They were all heavy drinkers. However, I would note that there were differences in terms of drinking, but the AUD negative heavy drinkers were drinking about 29 drinks a week, which is very heavy in terms of normative drinking. The AUD positive drinkers were drinking about 40 drinks a week. So this was a pretty severe group in terms of our AUD positive individuals. In general, they were young adults. They were recruited from the community. And what we saw was, at least in terms of their in-scanner decision-making characteristics, that prototypic difference in terms of AUD negative individuals showing substantially and statistically significantly shallower discounting curves relative to the AUD positive individuals. In terms of brain activity, we were really interested in developing a paradigm that would address what we thought was a gap in the field at that time, in so far as most studies were focusing either on identifying points of indifference out of the scanner and then focusing on very ideographically identified stimuli in the scanner, or just using a fixed set of stimuli in the scanner, but often winding up with highly unbalanced numbers of events in these designs. So we designed a paradigm that admittedly used a lot of items, but it allowed us to parse both impulsive versus restrained choices and also easy versus hard choices. Basically, we stacked the deck in the areas of the decision-making task so we would have more events close to what we predicted the points of indifference would be, and for would be able to have substantial numbers of events to look both at impulsive and restrained. That would be smaller sooner versus larger later versus easy hard. Easy would be choices that would be very far away from the point of indifference. So $99 today versus $100 in 2 months, easy choice. The choice before and after the point of indifference is reached, those are the choices that we think are more cognitively challenging, because then you're actually feeling indifferent to the immediate and the delayed reward. Our control stimuli were larger versus smaller amounts, both available today. So it was the identical paradigm, except instead of a delayed period, it was either smaller amount available today or larger amount available today, counterbalanced across the side of the screen. So we were able to really subtract out all of the activity associated with just larger versus smaller in monetary rewards. What we found was consistent with earlier work. Critical regions were anterior insula, medial frontal gyrus, posterior cingulate, dorsolateral prefrontal cortex, and supplementary motor area. This was the case for both impulsive versus restrained and easy versus hard. And where you see the differential activation, for red, it's impulsive only. For blue, it's restrained only. For yellow, it's both in both of these cases. And an area that we thought was particularly interesting was the dorsal anterior cingulate to supplementary motor area, where when we looked at the easy versus hard choices, when people were making those hard choices, the choices that were abutting the point of indifference, we saw significant activation in dorsal anterior cingulate. When people were making easy choices, we saw selective activation in supplementary motor area. And in between the two, we saw activation for both. And what this really looked like was basically what we refer to at this point as kind of an axis of conflict, in which people were experiencing clear conflict about their choice here. But when it was an easy choice, we were really just seeing very active motor activity, almost reflexive motor activity, taking the easy choice. And what we're seeing in terms of these were region of interest analyses, as were a lot of the early findings, but we're seeing that these are really compatible with the different networks that are increasingly being appreciated as being part of delayed discounting. In terms of our comparisons, we found a number of different regions were significantly different between AUD positive individuals and controls. The largest effects, interestingly, were in bilateral dorsolateral prefrontal cortex. And this was the case largely for restrained or hard choices. There weren't substantial differences between those effects. And what's interesting is that we found that individuals who were AUD positive were showing significantly greater activity in dorsolateral prefrontal cortex compared to individuals who were AUD negative, which was not our initial expectation. We thought that they're exhibiting behaviorally more impulsivity. We should see lower activity. It seemed like actually the executive network was being recruited more. It was working harder, even though the behavioral output was more impulsive. And this is actually consistent with work that's come out of Charlotte Bodiger's lab at UNC, and very recently out of Laura Ray's lab at UCLA. So subsequently, this is work that is just coming through the pipeline now. We've been interested in trying to apply this paradigm in a more translational way in the context of treatment. I'm going to take you back to a finding that I showed you earlier. This comes out of Warren Bickel's lab, and one of the earliest behavioral findings found that smokers show substantially greater discounting relative to never smokers and ex-smokers. And if you notice, the never smokers and the ex-smokers are virtually identical here. So that suggests one of two things. One, if you quit smoking, your discounting returns to normal. It's basically state-based, and there's a recovery. Or two, if you're a steep discounter, if you're highly impulsive, you will have trouble being able to quit smoking. And these ex-smokers are effectively people who did not have elevated levels of impulsive discounting to start with. Well, what we now know, this study came out in 1999, and there's now an extensive literature showing that in general, delayed discounting preferences tend to be more trait-like than state-like. They're stable over time, stable even to a year and multiple years in time in cohort studies. So stability seems to suggest that maybe impulsive discounting is a predictor of poor treatment response. And we've taken that on in my lab also. These are data from a study that I did with Chris Kaler at Brown, in which we were looking at delayed discounting as a predictor of treatment response for smoking cessation. These are our models predicting treatment. It was actually in the context of a clinical trial, so we included that variable, a variety of covariates, nicotine dependence, obviously. And what we found was that overall discounting was a significant predictor. We used actually 3 different magnitudes of discounting, and we found that the largest effects were for large and medium magnitude effects, and there was a non-significant relationship with small magnitude discounting. As an aside, when it comes to discounting, there are generally magnitude effects. The smaller the commodity, the more impulsive people are. The larger the commodity, the less impulsive they are. So if you use amounts that are too small or too large, you wind up with ceiling and floor effects in terms of the variability you see within your sample. What was particularly notable here was when we unpacked the data even further, if we looked at the participants who enrolled in the smoking cessation program, who quit on their quit day, did not smoke at every subsequent follow-up point, came to each post-treatment follow-up, and at each time were verified as being abstinent via carbon monoxide, we saw very shallow discounting rates, whereas if we look at the people who were already smoking on their quit date, we see very steep discounting rates. So here we see empirical evidence that discounting is a predictor of poor smoking cessation outcome. We've actually replicated this in a number of other studies, and increasingly in at least the areas of alcohol and cocaine use disorder, delayed discounting seems to be a robust predictor of treatment response. So what we have now done, and unfortunately I'd hoped I'd have some imaging data to show you today. I have the behavioral data from our recent study. We now combined our delayed discounting paradigm with a best practices smoking cessation intervention and are currently investigating the neural correlates of delayed discounting. Individuals in this study get 9 individual sessions of motivational interviewing plus CBT. They have a quit date on their second session. They get 8 weeks of nicotine replacement therapy, 21 milligrams followed by 14 milligrams, followed by 7 milligrams. And what we're doing is basically looking at neuroimaging predictors of smoking cessation outcome. What I have so far are our behavioral outcomes. So with what would be considered a high quality intervention, we see already what behaviorally the individuals who relapse, that is return to daily smoking by the end of treatment, show much steeper discounting relative to the individuals who have not relapsed at the end of treatment and are, no relapse in this case actually means are abstinent. About 43% of our sample was able to be in the treatment success group. And these are the discounting curves from in the scanner. So immediately after enrollment, participants had an MRI scan. They started treatment typically the next week. And so these are the preferences that we will now be using to unpack the neural activity associated with, to see which of the, what brain activity and what network activity is associated with success and failure in terms of discounting. So I'm going to pivot a little bit to some other work we're doing, moving away from functional neuroimaging to structural neuroimaging. And remarkably, there's actually been a lot more functional neuroimaging work done on delayed discounting than structural imaging. And the small number of studies that have been done have tended to be relatively small in terms of sample size, and they have really focused on the regions that have been implicated by the functional studies, which makes sense to an extent, but fundamentally bold signal and gray matter volume are different anatomical and neurobiological features. And so there are big gaps in terms of what's known about the structural correlates of delayed discounting. We've been using the Human Connectome Project data set to mine these data to identify structural correlates and address some of these limitations. One of the big issues is that in terms of gray matter volume, as most people know, there's a really big interdependence or autocorrelation issue, to the extent that gray matter volume tends to be highly intercorrelated both hemispherically and across the brain. So it's difficult without large sample sizes to really do brain-wide analysis. So what we did was we started with cortical parcellation and subcortical segmentation using the Desiccant Atlas to identify what are believed to be neuroanatomically discrete regions of the brain, and then we looked exhaustively at correlates of delayed discounting out of the scanner using first a covariate model, sex, age, income, as you'd imagine, and then total intracranial volume also to account for head size. And first we started simply with partial correlations looking across brain regions and including our covariate model to identify where there was signal, using error correction to then winnow down our pool to find where there was a reasonable number to include in regression-based analyses. And then after we included those variables in our regressions, we winnowed the regions that were no longer significant because they were basically implicated by virtue of multicollinearity. That is, they were confounded by the fact that they were associated with other regions. So this was a lot of basically taking large numbers of regions and trying to identify where unique associations were after our covariate model. And remarkably, all we identified were 2 regions in temporal lobe, which were somewhat incompatible with the functional literature. And these actually were 4 regions. They were bilateral because they were so highly correlated with each other. We just combined them into individual variables. These are the only variables that were predictive in terms of our parcellation and segmentation analyses. We then decided to move away from the Desiccant Atlas and simply look voxel-wise across the brain without any kind of predetermination of regions. And these are the regions, obviously cluster corrected, that were implicated with discounting. A lot of the regions that I mentioned before functionally that have been recruited, so dorsolateral prefrontal cortex, anterior insula, striatum, not implicated. But again, we see anterior middle temporal gyrus, entorhinal cortex on the left side, entorhinal cortex, anterior middle temporal gyrus on the right side. So what to make of this? This is what they look like in terms of regionally. These are medial and lateral images. Here you can see the anterior middle temporal gyrus. Here you can see bilateral entorhinal cortex. You can see almost perfectly symmetrical regions. And so we wondered what to make of temporal lobe, which is recruited in discounting functionally, but is by no means considered sort of a key region. And so what we did was we moved to the Human Connectome Project resting state data. So they have 60-minute resting state data on all 1,000 participants. And we generated seed regions and then looked functionally at the correlations between our anatomical regions in terms of activity during resting state. So what you can see, this is our seed region for right anterior middle temporal gyrus. You can see activity in posterior cingulate, posterior parietal cortex, medial temporal gyrus. And we did the same for entorhinal cortex. Again, I'm just going to show you on the right side, it's virtually identical to the left side. Again, we see here's our seed region, medial temporal gyrus, posterior cingulate, posterior parietal cortex. So what do we think? Well, it seems like the anatomical implication is by way of default mode network. And from a network standpoint, there's a lot of discussion about which networks are most implicated in delayed discounting decision making. I'd say the dominant thinking now is that there are 3 networks. The salience network that was discussed earlier, the executive control network, and the default mode network. And that seems to be most relevant here, that we're seeing, again, correlations between our anatomical region and these regions that are typically thought of as being part of the canonical default mode network. We then decided to do one more thing to try to elaborate the meaningfulness of these structural findings, and we went to the Neurosynth database that Damien spoke about earlier also. And here, unfortunately, within Neurosynth, you can't specifically focus on delayed discounting, and if you put in impulsivity, you get a variety of different tasks that are really a hodgepodge of things that sometimes are related to discounting and sometimes are not. But what we did was we again used our seed regions and looked at positive co-activation in 150,000 regions across all studies without respect to specific paradigms. And so here, again, you can see where we see coactivation with our structural regions are medial prefrontal cortex, posterior cingulate, posterior parietal cortex. And so, again, really regions that are canonically part of default mode network. So what we think that we're seeing structurally is quite different from what we're seeing functionally. And now we're not just looking at ROIs that come from functional studies, we are looking at brain-wide activity. And with over 1,000 people, we feel like we have sufficient power to detect small effects and not be concerned about being underpowered. So just to kind of recap some of these findings, the neural correlates of discounting in general include dorsolateral prefrontal cortex, medial prefrontal cortex, dorsal anterior cingulate, anterior insula, posterior cingulate, and posterior parietal cortex. These are really critical nodes within the executive control network, the salience network, and the default mode network functionally. In our data, and in the data from some other labs, we've actually seen that alcohol use disorder is associated with greater impulsivity, no surprise there, but greater activity in DLPFC during delayed discounting, and where we see significant differences in other ROIs, the same pattern is true. So greater or at least neural engagement despite more impulsive preferences. And then structurally, we see robust associations with specific subregions in temporal lobe in terms of gray matter volume. And that seems to be, we think, perhaps by virtue of the structural implication of those regions in default mode network in the larger perspective on networks recruited by delayed discounting. So I'm going to pivot. So that was work focusing on one form of decision-making, delayed discounting, which is a measure of impulsivity. Now we're going to talk about a different kind of decision-making, drug demand in addictive behavior. And many people are probably familiar with the notion of demand in economics. It's a foundational concept. It's fundamentally the amount of a commodity that is sought or consumed at a given level of price. In behavioral psychology, it is often used as a measure of the reinforcing value of the drug to the individual. And the way to best measure demand for any commodity is to conduct demand curve analysis. And what demand curve analysis basically refers to is examining consumption of a commodity across prices to see the shape of the decrease in consumption as cost goes up. So it's similar to the concept in physics that you can measure momentum to the extent that you can stop something. You use price to reduce consumption, and that's how you measure motivation. So here you can see on the x-axis we have our price, on the y-axis we have consumption of what could be any commodity. These are two prototypic people, a high demand person and a low demand person. And what's nice about demand curve analysis is that you really map the entire slope of this curve and you can carve out specific focal pieces. Intensity is the y-axis intercept, is consumption at minimal price or often zero price. At the other end of the demand curve is breakpoint, which is the first price that suppresses consumption entirely to zero. In between the two, this tends to be a curvilinear line, and where it moves from being inelastic to elastic, we refer to that as Pmax, or the price that creates price sensitivity. And more generally, a critical variable is the slope of this demand curve. That is, the overall decelerating slope independent of the amount of the commodity that's being consumed. And this can be analyzed in a number of different ways. We can look at it in terms of absolute terms, so the percent change in consumption relative to the increased change in price. So in thinking about this curvilinear pattern, when the slope is lower than 1, we think of it as being inelastic. When it's greater than 1, we think of it as being elastic. That basically means that consumption is going down faster than price is going up, or vice versa. And then we can actually quantitatively model it to get a single value, like our temporal discounting function, that reflects the price sensitivity of the individual to the increasing cost of the commodity. The other nice thing about demand curve analysis is it allows us to look at expenditure. So these are the exact same data, but now converted into how much money is being spent on the x-axis. I'm sorry, the prices are the same on the x-axis. The amount of money is now being shown on the y-axis. So you can see that as consumption goes down, expenditure first goes up during the inelastic phase of the demand curve, because consumption is going down slower than price is going up, but then it reaches a peak point, which we refer to as Omax or output max, and is the most that a person is willing to spend on the substance or whatever the commodity might be, before eventually it also goes down to zero at breakpoint. So demand curve analysis is what we think is a very powerful paradigm for modeling motivation to consume commodities, but in particular to consume addictive commodities. It gives us a measure of maximum consumption in terms of intensity. It gives us a measure of maximum expenditure in terms of Omax. It tells us where the behavior will stop in terms of breakpoint, and it overall gives us measures of sensitivity to escalating price. Now, you can measure demand in a number of different ways. Historically, this came out of the operant behavioral literature. It can be measured using progressive ratio schedules in rodents or pigeons, monkeys, other primates. It can also be measured in the human lab using lever presses or plunger pulls. We typically use purchase tasks, which are self-report measures in which we ask people how much they would consume at escalating levels of price. And we do this in part because it's much more efficient than doing laboratory protocols, but we also do it for ecological validity, since typically people are actually spending money to buy cigarettes, to buy alcohol, to buy cocaine. And so those cost-benefit choices are already part of their behavioral repertoire. And this can be done actually in a number of different ways. You can do it in an estimation-only format, so purely for hypothetical outcomes, or we do it in the human laboratory also, where people might get a bar tab of $15 or $20, and then they can choose how much they're willing to spend at varying levels of price, and then actually get access to the alcohol also. So in terms of the data that we get, I showed you prototypic data before. These are data from an actual study. We get basically prototypic data from human participants too. These are heavy drinkers, again, from actually the earlier study that I showed you, where we see a decelerating alcohol demand curve. The log coordinates obscure this slightly, but we saw significant differences in terms of alcohol demand between individuals at higher and lower levels of alcohol use disorder severity. And we see this basically, again, across drugs. So here are the alcohol demand curves. These are other alcohol demand curves. This is smokers making demand decisions, looking almost identical to our prototypic data. These are actually smokers, either regular control smokers or smokers with schizophrenia. So even in individuals who have other psychiatric comorbidities, we get orderly, lawful data. And we've been able to apply this to illegal drugs in terms of cannabis and also to cocaine also. So we're able to measure demand for addictive drugs, both legal and illegal. And when we look at the relationship to addictive behavior, there are very robust findings. So these are data from a study that my student Josh did, looking at a large cohort of drinkers, simply aggregating people by either an audit score of 8 or more or lower than 8. And as you can see, there are very large differences in alcohol demand, even after adjusting for number of drinks per week and other covariates. We see large differences in terms of individuals at higher levels of alcohol misuse relative to individuals at lower levels of alcohol misuse. These are data comparing individuals who were moderately dependent on nicotine to individuals who were either mildly or not at all dependent on nicotine, again showing significant differences. And here are differences in terms of cannabis disorder symptoms, no cannabis disorder use disorder symptoms versus any cannabis use disorder symptoms. These are slightly obscured by the log coordinates again, but what we see in terms of case control studies is very reliable differences in terms of drug demand. And my group has aggregated these data into a meta-analysis looking at correlations, this is for alcohol, between those focal indicators, intensity, Omax, breakpoint, and elasticity, in relation to measures of alcohol misuse. And what we see is that these are very reliable in terms of their statistical significance, and they range from sort of small to medium large effect sizes. I would say medium effect sizes in terms of associations, again, after adjusting for appropriate covariates. So this provides a framework for studying the reinforcing value of addictive commodities, and it also maps on level of severity among actively using individuals. one of the other things that we've done is try to incorporate, before I go on, I should say, often people want to know whether or not the hypothetical data map onto real decision making. And so we've done 2 studies looking at the relationship between purchase task preferences for hypothetical outcomes versus when one of the outcomes would actually be received in the bar lab. And what we found was that the demand curves are virtually overlapping. And we were also curious whether or not people will, 5 minutes, I better wrap up. All right, I'm going to skip ahead by a lot of slides, sorry. And I'm going to emphasize in the last 5 minutes what we found in terms of trying to develop fMRI paradigms to measure what's happening in brain when people are making these cost-benefit decisions about alcohol and other drug use. And the way we think about this is that the demand curve really allows us to think about motivation in a very precise way. When we look at the inelastic portion of the demand curve, we can see basically preferences for maximum consumption, where people are, we think, experiencing only perception of benefit and no perception of cost of use. When people are in the elastic portion of the demand curve, they're consuming, but at lower levels than they would prefer to. So we see this as being a good way of modeling both the perception of benefit and the perception of cost. And after people have reached breakpoints, when we see no more consumption, we basically see this as a way of modeling suppressed demand in which there's no longer a perception of benefit and only a perception of cost. Because I'm running out of time, I'm going to skip forward. We have developed an fMRI paradigm to look at this. In the scanner, what's nice to see is in our paradigm, we do see a period of inelastic alcohol demand followed by elastic alcohol demand followed by suppressed alcohol demand. And we've been able to identify a number of neural correlates, particularly, I'm going to skip to the key regions actually. Here in dorsolateral prefrontal cortex, striatum and insula, posterior parietal cortex, and posterior cingulate. And the last region that's particularly implicated seems to be angular gyrus, which plays a role in arithmetic and mathematical reasoning. So what we in general have seen so far in terms of alcohol findings is there is recruitment of frontoparietal activity in terms of decision making, consciousness, and perspective thinking. But when individuals are exhibiting that inelastic profile behaviorally, we see much greater insular activation, we see greater disengagement of the default mode network, and we see also recruitment of frontostriatal activity, suggesting an interplay between subjective reward and the external costs of drinking. Fast forward one more time into our tobacco findings. We found very similar results, and we've done a conjunction mask now aggregating findings across the 2 studies and identifying the regions that were common to both alcohol demand and tobacco demand. And that's the overlapping mask. Here are the common regions. Again, we see DLPFC, anterior insula, posterior cingulate, and dorsal ACC as being critical regions in terms of this cost-benefit decision-making phenotype in terms of addiction. So the last study I'll leave you with is what's nice to see. A lot of this work has come out of my own lab, but Meg Haney's lab at Columbia, focusing on cannabis use disorder, recently published a paper looking at cannabis demand and identified a lot of the same regions, looking at choices to smoke or not smoke. So again, we see DLPFC, anterior insula, and a lot of overlap in terms of the regions we're seeing for alcohol demand and tobacco demand. So we're not there yet, but we are zeroing in on what we think is a common neural profile associated with cost-benefit decision-making regarding substance use. In my last minutes, I will say I hope I've convinced you that these are useful ways of studying addiction. When it comes to discounting, we have an ever-growing literature on neural correlates of addictive behavior using very different methodologies and generating some compatible, some incompatible findings. We need to synthesize this work. We also need to think about how how different imaging modalities can provide complementary perspectives. We're not the only group that's found big discrepancies between functional correlates and structural correlates. And so I think we need to use morphometry, bold signal, probably PET, and ideally multiple forms of PET to identify neurochemistry, neurochemical correlations with discounting. And I think that that's where there's been a big gap so far. And ultimately, we need to move away from the cross-sectional studies that have been predominantly taking place and integrating the neuroimaging DD paradigms into clinical and longitudinal designs. Last thoughts about drug demand. This is really at the proof of concept stage. We've now published the work showing that we can study the neural correlates of cost-benefit decision-making. The big questions now are, what does that look like for people who have a disorder relative to controls? And what does that look like in the laboratory when, for example, we use cues, when we use stress, or when we use instructional sets to increase the value of alcohol or decrease the value of alcohol? So next steps we really see are taking our behavioral findings out of the scanner and moving them into the scanner in order to understand what the brain is doing at these varying levels of alcohol valuation. With that, I will skip forward to say thank you again to my collaborators, my funders, and everyone here for your time today. Thank you. Yes?
While I can see the absolute importance of determining these behavioral economics of the choice to use substances, but I'm actually more interested in treatment effects. Would you assume that the same paradigms and brain imaging procedures would be useful for examining contingency management rewards and the progressive schedule and the randomness of receiving the rewards, and that you could use the same models to fine-tune the most effective strategies and timetables for patients?
We certainly hope so, and the short answer is yes, that we believe that they have the same kinds of clinical applications. And I didn't present any of our clinical work today, but what we have shown, for example, is that naltrexone suppresses alcohol demand with our demand paradigm. So does topiramate in work that's still in preparation. And we've also shown that brief interventions, brief motivational interviewing interventions, also dynamically reduce alcohol demand in heavy drinking undergraduates, and the extent of those reductions are predictive of the effect of those interventions. So we think that they have a lot of promise as mechanisms of behavior change and as being efficient indicators of pharmacotherapy mechanisms of action potentially. To contingency management, your question was exactly my question, and so we were able to, around whether or not one could use it to predict response and then ultimately use it to titrate contingency management. We published a paper in Nicotine and Tobacco Research last year using a cigarette purchase task to predict contingency management performance in substance use disorder positive people who were trying to stop smoking. But it actually revealed results that were completely opposite to what we expected. So in the contingency management group, there was a significant reduction in smoking, just as you'd expect, but the cigarette purchase task was not predictive of their outcome. In the control group that got non-contingent vouchers, the cigarette purchase task was predictive of outcome. And so what we more or less thought was that it's capturing the reward value of cigarettes, but it's not capturing a lot to do with the reward value of money. And so if you thought that it was a really good way of capturing the financial side of things, it would be very promising for titrating the contingency management piece. And that, it's just one study, but our original hypothesis was that that was where the action would be because you're capturing the interplay of smoking and money, but it actually turned out to be, in a relatively large sample, the prospective associations were all in the control condition where you didn't see the same kind of radical decrease in smoking based on the contingency management. So great questions, and that we're trying to go deeper in brain, but the other idea is to hopefully take this experimental paradigm and really embed it in clinical context to look at things like mechanisms of behavior change.